Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge for April. Validate stack subsequence. So what this problem says basically is we get two integer arrays. One is pushed and the other one is called popped, and each have distinct values. This is important, and we want to return true if we can have the result of sequence of push and pop operation on a stack using these arrays. What does that mean? So basically we use the pushed arrays to push elements, and the popped arrays means that we pop them. So again, what does that mean? So we start out with an empty stack, and then first we push 1. And so the problem basically asks us, is there a sequence of operation respecting the order in these pushed array and then popped array, such that we can do push and pop operations and it will be a valid stack, right? So for example, in this first example, what we can do is we can first push 1, then push 2, then push 3, then push 4, and now we can use this pop operation to pop this 4. Now we don't have 5 pushed yet, so we push 5, and since we did this one, we pop 5. Okay, so you can see the order of pop works and the order of push works as well independently. And then we want to pop 3, so we pop 3 from our stack, we pop 2, and then we pop 1, and so that we pushed already. Okay, and so that will give us at the end an empty stack, which means we were able to push and pop all of them. So that's sort of the idea. Now in terms of the constraint here, it's not too big. The pushed array is actually just 1000, and then popped and pushed array have the same length, so we don't have a problem of mismatch where length is not the same, and so it's not possible. We don't have that problem. And then the elements are also unique. So how do we tackle this? Okay, so let's try it on an example, the first example here, and see if we can identify it. So what we can do is just try to imitate a stack where basically we go and push, but we also want to pop. So as soon as because the elements are unique, then as soon as we encounter, that's what the problem says, the values are distinct in each of these arrays. So as soon as we encounter a 4 in our top of our stack, we should pop it, because we know that that's the only place where it will be, right? And so we push 1 and we check because this is the order of the pop, so we have to pop 4 first before any other elements. So that's why we start out there. And so we check, is 4 on the top of the stack? No. And so let's continue pushing. Now, is 4 on top of the stack? No. So let's continue pushing. Is 4 top of the stack? No. So we push. Now, is 4 top of the stack? Yes. So we pop it off and we move, because the next thing we want to pop is 5. And so now again we do the same thing that we were doing before, is we go to 5, is we add 5 to the top of the stack. Is 5 top of the stack now? Yes. And so we pop it off and move our pop pointer. Now we say, is 3 top of the stack? Yes, right? Because those were removed. And so we remove it. And then since nothing else to add, we just check again. Is 2 top of the stack? Yes. So we pop it off. Is 1 top of the stack? Yes. So we pop it off. And then at the end, how can we tell if these were valid operations? Well, if they were valid operations, that means we push everything and pop everything, which means basically that the stack, since we can guarantee that we will push everything, because we'll just do a loop on the pushed, we can just return if the stack is empty. Then that means we were able to pop everything, and by default we will make sure we push everything, right? So that's the idea. Now let's take a look at it on the second example, just to make sure it really works. So the second example is pushed is going to be 1, 2, 3, 4, 5, and then popped is 4, 3, 5, 1, 2. Okay, so let's see so we push 1. Now is 4 top of the stack? No. So we push 2. Is 4 top of the stack? No. We push 3. Is 4 top of the stack? No. We push 4. Now it is, and so we pop it off. So we pop off 4. We move our pointer to 3. And now is 3 top of the stack, yes. And so we pop it before doing anything else. So we pop this, we move to 5. Is 5 top of the stack? No. And so we push 5, and now 5 is top of the stack, so we pop it off. And now we are done with push it, so we just continue checking if we can pop. Can we pop 1? No, because it's not top of the stack, and so we have to stop because we can't pop 2 before 1, and so we have to stop. We can't pop 2 before 1, and here we have to pop 2 before 1, and so there is a contradiction. And so at the end we'll find that our stack is not empty, and so we'll return false. Okay, so that's roughly the idea here. Pretty straightforward. Now, in terms of time complexity, what is the time complexity here? Now, what you saw is we will go through the pushed elements, which is O(n) in terms of this one. But for each one of them, we go over also the popped element. But here we pop at most overall O(n), right? In total, right? Not just per iteration. In total, we'll pop up O(n). So this is actually a plus operation. It's not a multiplication because overall we'll pop only O(n). So overall time complexity is O(n). And then in terms of space, we are using this stack, and so it's O(n) space as well. Okay. Yeah, and that's pretty much it. So now let's implement it and make sure it passes. Okay, so what do we need to implement this? First, we need our stack, right? So this would be something like just an empty stack. And then we need to go through push it, as we said in the overview. So we need to go through push it array, and we want to, each time we want to add to the stack. But we also want to check popped, right? And popped, you remember in the overview, we kept moving the index every time we pop. And so we need to have the index that we move because we are already doing the loop on the pushed. So here we want to check is the current element where we are at in popped. If it's equal to the top of the stack, we want to pop the top of the stack. That's what we did. And so that's what we want to do here. And in that case, we want to pop. But we also just popped this element, so we want to move the index to the next one. And so we want to do i+1 here. Now you may say, why are we doing while? Because maybe the previous element we pushed should be popped right after this index, and so we want to keep doing it before putting any new element on top, right? And so at the end we guarantee that it worked if the stack is empty, right? So if the length is empty, you could also do just not stack in Python, but this is more explicit. And that should be it pretty much. So let's run it. Yeah, here we want to make sure that the stack contains an element, right? Because if the element is not pushed yet, like the case with 5 in this example, if the element is not pushed yet, then it won't be here. And so and the stack may be empty, and so we just want to make sure that it's not empty yet. So submit, and that passes. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.